So the reason that the probability x is between 0 and 1 is 100% is we're saying, what value do we need to pick here on the x-axis to contain 100% of the area under this curve to the left of where we are? So if you did 0.2, we would be looking at all the area to the left of 0.2. If you did 0.8, we're looking at all the area to the left of 0.8. And you'll notice if you pick 1, then because everything is 0 past this point, let's make the dinging stop, or else we go to jail, dinging jail. Okay, so if you're at x equals 1, that's right here, all of the positive parts of the function are to the left. Everything past 1 is nothing, and so there's no area to the right of 1, all the areas to the left of 1. This probability is 100%. So you guys all figured that out, or most people did. Very good. What about the other one? What about the other one? 0 less than x less than blank. And this time it's a little bit more split. So some people picked 1/2, and some people picked 1 over square root of 2. And again, the question we're asking is, which value of x should you pick to trap half the probability? And if you picked a half, if you picked x equals a half, you were saying, let's draw a vertical line right here at x equals a half and compare the area between x equals 0 and x equals 1. So everything over here. Let's draw a picture of this. Let's draw a picture of this. Can I copy this picture? Copy image. And then let's paste it. Okay, here we go. So if you chose x equals 1/2, you are talking about this area. 0.6, 0.5 must be here. X equals 0.5. And you're talking about everything over here. And you were telling me, if you chose 1/2, you were telling me this area is half of the total area. This area is half the total area. And the reason this half is the right-hand side of the equation. The probability of 0 less than x less than question mark is a half. We wanted the area to be half, the probability to be half. Is x equals 0.5 the right answer? No. That's not half the area. Look, this side is bigger than that side. The green area is definitely bigger than the orange area. Because look, it's just like taller. In fact, I can tell you how much taller it is by drawing a sneaky triangles like this. If you draw some sneaky triangles, okay, you gotta do a little bit better of a job. Wait, Gary.
You want my ruler?
You have a ruler.
I have a ruler.
This is amazing. Look at this juxtaposition of analog and digital technology. You take your ruler, you put it on your tablet. Oh yeah, that's next level. All right, now it's pointing a little bit up, but that's the best we can do. And then another one like this. Okay. And you have to imagine I did it a little bit better. But now I've divided this total region into 4 regions, and I hope you can see all the regions are equally sized. So this area is not half the total. This is wrong. This area is actually 1/4 of the total. So the probability that 0 is less than x is less than a half is 1/4, not a half. If you want to get half the area, what is the right answer? It's actually what most people got, which is it's 1 over square root of 2. So those people got the right answer. Over here, 1 over square root of 2. And why is it 1 over square root of 2? Let's find out. So 1 over square root of 2 is going to be right. Let's try another copy of this. And actually, I'm going to do the more general problem. I'm just going to pretend we're going up to some arbitrary value x. I'm going to call this lowercase x. And let's find the area over here. So I'm really calculating the probability that x is between 0 and lowercase x. Let's just do this. And we'll see that when we put in 1 over square root of 2, that we get a value of a half. That's what we're going to do. And you can kind of do this the more explicit way or the more implicit way. You're going to get the same answer either way. Let's do it the very explicit way. Is what is the equation of this line? Equation of line. Okay, and we know it's a linear equation, and we see that it goes through 0. So it's y equals mx for some value of m. Y equals mx for some value of m. There is no b because the intercept here is 0. What is the m value? Well, the m value is this, m. And that's because if you plug in x equals 1, you get y equals m. So the height of this triangle is what I'm calling m, the solution. Okay, and what should that be? Well, the total area is supposed to be 1. The total area is the total probability is 1. And the total area, on the other hand, is base times height divided by 2. Base times height divided by 2, which is 1. The base is 1, because it goes from x equals 0 to x equals 1. The height is m. M times 1 divided by 2 equals 1. Or another way to say that, m equals 2. M equals 2. So this is the equation, y equals 2x. This is the PDF where the function is y equals 2x between 0 and 1. And so what is the area of this triangle? Well, it's a triangle. It's base times height divided by 2. Now I'm talking about this orange triangle over here. This is the orange triangle I'm talking about. The base is x. X. From there to there is x. What is the height? Well, that is the function that we're looking at. And we said the function is y equals 2x. So the height is 2x. And we divide by 2 because we divide by 2. And then you get a really nice equation, which is x times 2x divided by 2 is x squared. So a very nice formula. And we did this all the explicit way of finding this thing. Once you get to a final answer that is so beautiful, like x squared, you can look at it and say, oh, we could have done that an easier way. And the easier way is to just notice that we have scaled the x-axis by a factor of x. And because it's a similar triangle, when you scale the x-axis by a factor of x, you also scale the y-axis by a factor of x. So the ratio of this orange triangle to the big triangle that we want, the side lengths are in proportion x, and therefore the areas are in proportion x squared. So you could have been a little bit more sneaky and skipped all the steps by using the fact that the area is like length squared. Length squared. So an x factor in length is an x squared factor in area. In length goes to an x squared factor in area. So you could have sort of skipped these calculations. But if you want to do it the hands-on, honest, digging a hole in the ground way, then you just do all the calculations. And the answer was x squared. This is very similar to what we did last class. Any questions? Yeah. Why is the height 2x? So remember, we were finding this y equals mx, and I solved for m equals 2. So the equation of this line here is y equals 2x. I know it has to be y equals mx because it is a line and it goes through 0. So it's y equals mx plus b, and the b value is 0. So it's y equals mx, and then I calculated over here, what does the m value have to be? That was this little calculation, is solve for m. That was what I did. And when I solved for m, I got m equals 2. M equals 2 is the exact right answer to make the total area equal to 1. If the total area is not equal to 1, it's not a real random variable. So because of this fact that the total area equals 1, because RV, the total area has to be 1, that let me solve for m. This is very similar to what we did at the very end of last class. I think there was one where we told you the height and didn't tell you how long it was. In this one, I told you how long it was, and you had to solve for the height. But same concept. Any other questions? Okay, so what is the answer to the question? Please solve for 0 less than x less than lowercase x equals x squared. If you've got to solve the probability of 0 less than x less than lowercase equals x equals 1/2, then you get x squared equals 1/2, also known as x equals 1 over square root of 2. And that is why the final answer was 1 over square root of 2. It seems like a lot of people got this right, maybe by process of elimination, or maybe they figured it out. But this is a thing that happens in triangles, is the areas go like the square of how far over you are. All right. Any questions or comments about this? Yeah.
Sorry, can you explain the last part again?
The last part, yeah. So in the mathematized question, I said, please figure out what to put in here to make the probability equal to 1/2, right? And we just figured out that whatever you put in here, you're going to get the answer x squared. So the mathematized question said, solve for the area equals 1/2. And we know the probability is x squared. So this is like solving the equation x squared equals 0.5. Please solve it. And then we did that. We took the square root to solve it, yeah. Okay. There's two definitions that come with this problem and that you should know. One is the median. So here's a little math definition for you. The definition. The median. What is the median? If someone says the median of x. Let's say median a few more times. Median. It's the number. It's the number. Let's call it lowercase x. So that what? The probability that capital X is less than lowercase x equals 1/2. So for every random variable, no matter what random variable it is, you can always ask this question. What is the thing you should put in so that the probability is 50%? That special value is called the median. We've proven that the median of this guy is 1 over square root of 2, which I believe is like 0.7. Yeah, that makes sense to me. And medians are useful for some things. That's the definition of the median. You'll notice actually that in the real definition, you don't start at 0. That's because this random variable happened to start at 0. But in the real definition, it starts at some arbitrary number. So that's just the definition. For our question, it was the same thing. But there you go. Questions about the definition of the median? All right, not too exciting. You've probably heard of medians before. Do be a little bit careful. You might have heard of the definition of a median for a list of numbers. Like I have a list of 12 numbers. What is the median? This is the definition for a random variable. So the median of a random variable. And they're related, but slightly different. So don't get them mixed up. Okay. There's one more definition, which is something called a CDF. You've seen the PDF. Now you get ready for the CDF. The CDF is the cumulative distribution function. What's the cumulative distribution function? Also called the CDF. So the probability density function, the PDF, was this bad boy, whose areas give us the probabilities. The area under the density function gives you the probabilities. What is the CDF? The CDF is this function that just gives you the probabilities directly. So it's the function, let's call it f sub CDF of x. It's the function, the probability x is less than x. And the example, we just did the example. The CDF for the example, for the mathematized example, is f CDF. The CDF of the random variable we were thinking of, it was x squared. X squared. Let me write it a little bit lower. F CDF of x. It was the function x squared. So yeah, we just did it. We calculated the probability that 0 is less than x less than x. This 0 in this problem doesn't matter because the probability of being less than 0 is 0. So we just did it. It's x squared. Any questions or comments about that? Okay, so morally speaking, it is x squared, but there is an issue. If you write this on your page, you have committed a sin. This is like the probability police will come arrest you if you write down f of x equals x squared. And that is because, look what happens. What if x equals 2? What if x equals 2? Then you get the f CDF of 2, according to what you wrote, that's 2 squared, and 2 squared is 4, and that's supposed to be the probability that x is less than 2. Uh-oh. You just told me the probability that x is less than 2 is 4? No. Straight to probability jail. So the CDF, it is x squared, except for it's only x squared for the x's that make sense. So when we did our calculation, we were assuming that x is between 0 and 1, and when you write down the CDF, you better write that down as well. So this is actually a piecewise function. It looks like it has 3 branches. It's x squared if 0 is less than x less than 1. So for the actual values we care about, it's x squared. What happens if x is less than 0? That's something's going to happen. And what happens if x is bigger than 1? Something else will happen. See if you can fill it in. I'll tell you in a second. But if you've been following along, you'll have no trouble filling these in. 0 and 1. So the probability that x is less than 0 is always 0 for any value. And the probability that it's between 0 and whatever is always 100% if that whatever is 1. So for example, this is wrong, but the probability that x is less than 2 does equal the thing I actually wrote, which is 1. So as long as you plug in something larger than 1, you're always going to get 100%, which is just saying exactly what we started off our class with, that there is no chance of it being anything other than something from 0 to 1. If you're bigger than 1, there's a 100% chance that the random variable will be less than that. Okay. That's the definition of the CDF. Any questions or comments about the CDF? Yeah.
Sorry, can you just
Yes, I can go back. Yeah, here's the function, the CDF. Let me say one very last thing. If you're not in Math 1200, you can, or you don't like calculus, you can shut your ears for the next thing I'm going to say. It's a little bonus thing. The CDF was x squared. The PDF, what was the PDF? The PDF was the function 2x. CDF, x squared. PDF, 2x. What is the relationship between x squared and 2x? If you're taking a calculus class, you know that there's a relationship between the function x squared and 2x, which is doing the derivative. And the CDF and the PDF are related by the derivative. If you keep taking stats classes, you will learn that. In this course, you do not need to know this relationship, but it is cool to know why are they torturing you with calculus, because it's useful for stuff like this. All right. So there we go. We got CDF, we got median. We did a good example. Questions or comments? Okay, I'm going to hand it over to...
Could I have a
Oh, yes, yeah, all right.
If you took two random observations on this distribution you have here, what's the probability that both would be less than the median?
Oh, that's a great question. So you want me to, this is like the kind of question we can ask. So if we do x1 and x2 are samples of x.
Independently.
Are they independent? I was going to ask.
Yes, they're independent.
All right. They're independent samples. Independent samples. There's a cool acronym for this, which is the acronym IID. IID. IID stands for independent and identically distributed. Independent and identically distributed. So these are two IID samples of the thing. And you want to know what is the probability that x1 is less than the median? Let's call it the median. And x2 is less than the median. Let's throw the squiggly brackets on the board. This is the question. This is a great question. Is there some kind of way to simplify this to get an answer? Should we make that a homework problem?
No, let's solve it now because I got a tougher question for you.
Oh no, okay, if it's gonna have a tougher one, we better solve this. So, we want the probability that something happens and something else happens. Thinking back to what we did before the first midterm, you got the probability of two events. How on earth are we gonna simplify this? And then we're gonna recognize, oh, they're independent. And this is, if you have two independent random variables, then these two events are independent. So it's the probability that x1 is less than m times the probability that x2 is less than m. All right, so we've made some progress. We've simplified it. And now we say, what's the definition of a median? Well, the median is defined so that this probability equals a half. So this is a half. This is a half. This is a quarter. A quarter. So if you have two independent things and you want them both to be less than the median, the chance is a quarter, because the first thing's got to be less than the median, half. Second thing's got to be less than the median, another half. They're independent, so they multiply. Did we get it? What's the follow-up question?
Oh, what's the follow-up? So I got a problem, and it's got exactly that PDF that you're working with, and it's pretty easy for you to get me the probability that x is less than 0.6, right?
Uh-huh, yeah, sure.
You could do that very easily.
Yeah.
In fact, that was just 0.36.
Yeah, 0.6, whatever you want to do, we just square it. We square it. Yeah.
Okay. If I took 5 observations, 5 independent observations, what's the probability that exactly 3 of them would be less than 0.6?
This is great. Okay, so part 2. Now it's getting hard. Now we're mixing things. Okay. So question 1. Take 2 IID samples. And now it's a good thing we have this nice acronym, because question 2 is going to be a snap to write down. Let x1, x2, x3, x4, x5 be IID samples. What is the probability? The probability. Exactly 3 are less than the median.
Well, I went with 0.6. 0.6, but if you want.
Oh, sure. Okay, less than 0.6. Even.
You're making it too easy.
Okay. That 3 are less than 0.6. This is a great question. It combines what we just did now with stuff we did before. So on the face of it, this looks like, oh my god, there's all these random variables and things. But you have to recognize the pattern here, that there are 5 things, and we're asking the question, what is the probability that exactly 3 of them are less than 0.6? So one way is this could trigger your spidey sense, and you could remember, hey, wait a minute, we did this kind of question where there were a bunch of things, and we were counting how many of the things happened. And that was the binomial random variable. So answer. The number of things, let's say a number of RVs less than 0.6 is binomial. It's a binomial random variable. So you have to remember this, that when you have independent things and you're counting the number of them in a fixed number of trials, that's going to be a binomial. So the 2 conditions are the things better be independent. Things independent. Independent? Are they independent here? Yes, they definitely are. The I in the IID was the independent. And what else? There were a fixed number of trials. Fixed number of trials. The number of trials here is 5. There are 5 random variables of trials. Here it is n equals 5. Okay. What is the probability? The probability of success on each trial. Probability of success. Oh, this is the hardest part of the problem. How do you spell success? Suck. Success equals the probability that x is less than 0.6. So we wanted 3 of them to be less than 0.6. So what is the chance of one of them coming up? Any individual one, x has to be less than 0.6. That is 0.6 squared, or 0.36. We did that earlier in the problem. So this is like you're putting layers on the different things in the course, right? We got probabilities on probabilities. We calculated this probability one way using areas and things like that. And now we are plugging that in to the other part of the course where we did binomials. And the binomials have a probability p of success. So in this case, this is a p equals 0.36. P equals 0.36. So we got n equals 5. We got p equals 0.36. What is the question asking us for? The probability is exactly 3. So the question is saying, what is the probability that a binomial random variable with n equals 5 and p equals 0.36, what is the chance that that equals 3? So this is the original question. And you see I had to unpackage all the layers like an onion to get down to this point. N equals 5 and p equals 0.36. And then I remember what the formula is, or you derive it in your head, or you look in your notes. Oh, you make sure to write it on your study sheet for the exam. Okay, 5 choose 3 times 0.36 to the power 3 times 1 minus 0.36 to the power 2. Okay, very good. That's the answer.
I'm happy.
Well, the one thing I think you're going to be upset by, Gary, is success. Okay, question over here.
Why do we square the 0.6 again?
Yes, this is a great question. The reason we square the 0.6 is actually this 0.6 squared is whatever the CDF of the random variable is. So the real answer is this is f CDF of x. It's whatever the CDF of the random variable is. It's the chance that each individual guy works out to 0.6. And earlier in the problem, we calculated that. So I used a fact from earlier. If you hadn't done that earlier in the problem, you would have to do it now. But fortunately for us, I did it a long time ago, all the way up here. We calculated the probability that it's less than x is x squared. So I'm saying by the thing we did earlier, in this particular problem, it was, this is earlier, we saw this was x squared. And so this function, x squared, when you plug in x equals 6, x equals 0.6, you get 0.6 squared, which is this. So I'm sort of importing knowledge that we did earlier. In any particular problem, they would have to tell you about the random variable x enough that you would be able to calculate this. In this particular problem, that's what it is. Yes, this is a layers on layers problem. I remember when I took first year physics, we did two separate things in first year physics. One thing we did was buoyancy, so you like put something underwater, how much force does it have? And then one thing we did was simple harmonic motion, so you have something bouncing on a spring. And on the exam, they said, what happens if you put an ice cube and it bobs up and down? Tell me about that. And I was like, oh no, we have to combine. Okay. Question here.
Is testing going to be cumulative or only on random variables?
Well, so the focus is on random variables, but as you're seeing, when you do random variables, you have to know about events and things. So a great example, maybe this question too, this one was involving binomial random variables with the other stuff. But question 1, I think, is a quintessential example of, it's really a question about random variables, but look, halfway through, we had to do independence of events, right? And independence of events we technically did before midterm 1. This is a great question that would be on midterm 2, because you need to know both, right? You need to know random variables and events to be able to calculate it. Yeah?
Are you going to give us a big problem sheet?
There is a big problem sheet that's in progress, right?
It's in progress.
It's in progress.
It'll be out by the end of the week,
Should be out very soon.
but it'll
Yes,
come up as quick as possible.
that's right. Yeah, and it's not till Wednesday, right? Like a week from today?
It's a week from what? Yeah,
A week from today.
a week today.
Yes. Other questions? Yeah. Are you allowed a crib sheet? Yes. Same rules as midterm 1. Of course, you can bring a different crib sheet, and you should.
No, additional rule.
Ooh, new rule.
New rule. For the first test, we allowed 1 crib sheet.
Oh, okay. 1 page.
Second one, we allow you a second page.
Oh, you can bring 2 pages. Okay, there you go.
2 pages. So if you want to take your first one, or whatever you did on the first one, add a
Okay,
second
there you go. You can add a page if you want. Very exciting. There was one more question here somewhere?
And we're going to allow 3 pages for the final exam.
Oh, okay.
Yeah.
Any other questions or comments?
Yeah, I got another question.
Oh my goodness. Okay, what is the other question?
If I took 2 observations on this distribution,
Yeah.
could you tell me the probability that, well, I'll work with 0.6 again, of 2 observations, one of them was less than 0.6 and the other was greater than 0.8?
Are they IID?
Yes.
Okay, let's do it. Let's write this one down. Question. X1 and X2 are IID. We're making heavy use of this IID. We better write this one down. Okay. What is the probability? The probability that X1 is less than 0.6.
No.
Oh, you want one of them.
One of them.
Oh, I see. Okay, I see. Okay.
Insist on X1.
Well, when you said one of them, I got excited because I had an X1, you know?
Yeah, I know.
Probabilities. Probability.
Ability.
What do we need? 1 is less than 0.6. The other, what did you want the other one to do?
The other is greater than 0.8.
Greater than 0.8.
That's
Ah, yes. So one of them is less than 0.6. The other is less than 0.8. This is another fantastic question because, look, we got these random variables x1 and x2, and we have to manipulate them. But the answer is actually a midterm 1 type question where it's saying we got 2 things, and we want them both to happen. How can you do it? It turns out there's more than one way. So this one, I think there are 2 ways. This is the answer to this question. There are 2 ways it can happen. 2 ways this can happen. And this is like the simple combinatorics or tree stuff we did before midterm 1, which is you could have option 1. You could have x1 is less than 0.6 and x2 is bigger than 0.8. That's one way to do it. One of them is less than 0.6. The other is bigger than 0.8. Or you could have option 2, which is it comes out the other way around. x1 is bigger than 0.8. And x2 is less than 0.6. So again, this is some kind of weird hybrid of the midterm 1 stuff. 2 options, events, intersections, ways things can happen, and what we're doing now with random variables, because the things are themselves random variables. What are the probabilities of these 2 things? The probability of option 1 is the product of the probabilities. It's the probability x1 is less than 0.6 times the probability x2 is bigger than 0.8. And that's by independence. By independence. So once again, you have these two observations, independence of x1, x2. The probabilities multiply. So if you ask for something involving x1 and something involving x2, the probability is the product. The probability of option 2 is the same thing, but the other way around. Option 2 equals the probability x1 is bigger than 0.8 and x2 is less than 0.6. In this situation, these are both the same answer. Both are equal to what? Well, less than 0.6 we've done. 0.6 squared. What's the probability you're greater than 0.8? And this is another trick we're going to do. The chance you're bigger than 0.8 is 1 minus 0.8 squared. So the probability x is bigger than 0.8 is 1 minus the probability x is less than 0.8, which is 1 minus 0.8 squared. So again, taking what I have, which is this CDF function, the chance that you're less than something, I know that's the square function, and getting what I need, which is bigger than 0.8. So both are equal to this. So a final answer, probability of thing Gary wanted. It's the sum of the two probabilities, option 1 plus option 2. Option 2, which is twice 0.6 squared times 1 minus 0.8 squared. So very nice. Oh, you could even add a little note here. These are mutually exclusive events, so the probabilities add. Events. So probabilities add. Watch out for that, aka disjoint. So that's why it was okay to add up the probabilities. So this is some kind of weird combination question of stuff we did before the midterm and the new stuff with random variables. What a lovely review question. Yeah.
I have a question for when it comes to the problems that you guys are posting this weekend. Will you guys post solutions for those questions at the same time, or when will they be?
I think the solutions will come later. The problem is if we put the solutions out at the same time, there's too many students who read the solutions. And then this is like I always say, this is like you go to the gym and you watch the other people at the gym lifting weights and you're like, I did it. Because it doesn't work. You gotta lift the weights yourself. You should feel free to post. You know, you can ask people for help or come to our office hours. There's a lot of good online resources and things too. So you should feel free to, once you try it, to look up a solution. But do try it on your own first. Yeah. Fantastic. Okay.
Thank you.
Gary, I have a question for you, Gary.
Okay.
How do you use the R language to do some of these things?
Oh, well, we're going to get into some R.
Okay.
Now. Yes.
That'll be good, because I'm sweating over here and I need a break.
You need a break. Well, thank you. You have done lovely things. Okay. Now, where did the stuff go? Okay, I'm gonna go straight to R right now. Am I on the HDMI?
You are. You're live.
Okay.
Well, let me give you the microphone.
Yes.
Lovely.
Okay, we're going to jump in and do a few simple things in R, but they're kind of fun things in R. And then, given our time, we'll probably have to get into a larger discussion on Friday of what is it that we actually just saw. So before I go on to the R, I'm just going to discuss a little bit more about uniform distributions, continuous uniform distributions. I could also discuss discrete uniform distributions, but I think we're just going to say a couple words about, come on dot cam, what's your problem? Oh, it's my problem is I hadn't turned on the dot cam. My fault. It needs some thinking. There it goes. So, continuous random variable x with parameters, oh, I can call them various things. I'm going to call them A and B. I was going to call alpha and beta, but you know, like mathematicians and statisticians, they like their Greek well, actually, why not use our Greek alphabets? Because that way we won't get it confused with alpha and beta. With parameters alpha and beta, and the idea being that, you know, we can have any distribution, and there's going to be some minimum for which f of x is greater than 0, or approaching f of x, is, as you get close to that alpha, the f of x is greater than 0, and you've got a beta. Okay? And the idea of continuous uniform distribution is that you put that across there. Total area equals 1. The area under the curve is equal to 1. And so going that way and that way, this is where your x is. And I could put this up anywhere, it doesn't really matter. Okay, but this is f of x going this way. And in order to have a total area under there to be equal to 1, if the length here is beta minus alpha, and we can see that the length beta minus alpha, then the height has to be equals 1 over beta minus alpha. Okay? So the idea being that the uniform distribution can be stretched over any interval where there's some minimum value and some maximum value, but the idea is that of the continuous uniform distribution, you take any interval of a set size, and no matter where you go in that interval, the probabilities are going to be the same. Now, the unit uniform distribution is on the interval 0 to 1, so its height is 1. Okay, it just forms a little square. Well, it depends how you stretch it. It could be a rectangle, but the point is that your lower value is 0, your upper value is 1, and therefore the height has to be 1. Okay, so that's just kind of setting up a couple of things for working in R now. Okay, so here's what we're going to do in R. I'm going to any questions there so far? Okay, kind of got that. And there's some other things we could say about that, but we don't need to say it right now, because we have so many things we want to say before you leave today. Okay, so there are, just remember, when we did the binomial distribution, we had various functions. There was a p-binom function, there was a p-binom, there was e-binom, and then there was an r-binom. And what r-binom generated was random binomial, random variable values for particular values of n and p. Okay, so we generated random values there. We can also generate random uniform values, and I'm going to use, we're going to look at our unif, and I can generate a bunch of them. And by default, if I don't put an alpha and a beta value in there, it takes them on the interval 0 to 1. So when I run this, I expect 10 random values between 0 and 1, and it's just picking them totally at random over that interval, and that's what I did. Okay, wing, and there they are. 10 uniformly generated and independently generated uniform random variable values on the interval 0 to 1. Okay, so those are kind of cool. Okay, what else do I want to do with this? Okay, well, if I was to run this again, the little suckers, they come up with different numbers on me, so this is kind of inconvenient. Okay, so I'm going to generate some extra values, and I'm going to go back and I'm going to call those x. And, okay, so if I run this now, you see I've got those little, those uniform values trapped. Now, I'm holding on to them. Well, 100 isn't very interesting to me, and I don't find it a lot of fun. I like to have fun, so I'm going to increase my number of generated values. And I could generate it, well, where would I like to go to? 100, 10, 100, 1,000, 1,000. 1,000 is pretty big. 10,000 is even bigger. 100,000 sounds like even more fun. So I'm going to go 100,000. I'm going to generate 100,000 of these values. And I will warn you, do not type the X at this point, because you've generated 100,000 of them, but I could tell you that if I asked to just see 5 of them, for example, I could do it this way. Oops, I didn't do a capital X, I got a capital X, and then I'm going to do 1 to 5 in brackets. So that's the first 5. Oh, what do you mean? It's, what did I do? Oh, I got the wrong bracket at the end. It should be square brackets here. 1 to 5. And so those are just the first 5 values, okay? And you can pick any other pair of numbers that'll give you those numbers, but you do not want to dump out all 100,000 of them. Okay, so if I was to look at the distribution of those, what we call the empirical distribution, I could do a histogram of these. And I'm just going to ask for a histogram of X. And again, you know, there's a little variation there because it is a random sample there, but you can see it's more or less even across the top there, not perfect. I could generate some extra bins there. Maybe I want more bins. I like bins. Bins are fun. So if I want to get more bins, instead of doing however many it did there, maybe I'll do breaks equals 100. Okay, so, oops, what did it say? Breaks equal, oh, I got too many brackets. 1 minute, too many brackets. There we go. Okay, so breaking up into little tiny bins, but again, you see, like, everything's random and then it's gathered into those bins. Okay, fine and dandy. That's kind of cool. Now, I did that as an X. Let me generate another group of these random variables, but I'm going to call this group will be called Y. Why is it called Y? Because it's called Y. Okay. And I could have done a histogram of those little suckers too. Yeah, let's do a histogram of Y and a little bit of things going up there. And got that. Okay, so what I want to do now is add the X's and the Y's. And what's this going to look like? Think about what it's going to look like. We got these 2 things that are basically just uniform distributions. And so I'm going to do the histogram of x plus y oh my goodness, what did I break? I must have broke something. Darn thing looks like a triangle. Okay, so that's it for today. Next day we start off and discuss why we got a triangle on this x plus y.